Hello, welcome back. We are talking about data analysis and we have talked about functions in the previous session. So go back if you want to revise this, if you want to remember what a function is and how functions work. And we also talked about the important difference between linear functions and nonlinear functions, where the linear functions are predictable and calm and develop in a very smooth way, while the nonlinear functions are a little more unpredictable, a little more violent. They can develop very fast for particular ranges of inputs, or they can slow down, and therefore they are not always as easy to predict and to control as the linear functions. Now, on the totally other extreme of non-predictable behavior would be a truly random process. What's a truly random process? For example, gambling in an ideal casino. It's not truly random, probably in really existing casinos. You're being cheated, especially if they're online. But if it is an ideal casino, let's say a platonic version of a casino, then it would be a truly random function. So when they throw this ball into the roulette wheel, then there are all these mechanical factors, all these mechanical forces that act on this ball that make its trajectory truly random, again, ideally. So you have the temperature, you have the elasticity of the ball's surface, you have the friction with the rim of the roulette wheel, you have air currents in the room, you have the temperature emitted by the body of the person standing beside the wheel, and this moves again the air molecules which affect the ball. You have the speed by which the ball was thrown, and all these are different parameters that are so complex, things like the airspeed of the movements of air or the movement of the person beside the roulette wheel. There are so many factors that we cannot process them, we cannot predict them, and so we feel like this process is truly random. You have no idea what will happen. The same when you throw dice, right? If they're not manipulated and the surface is more or less a normal straight surface, then there are so many factors about the stability of this cuboid object on this hard surface that it's impossible to predict how it will fall. And so we again feel that it is truly random. Now, whether these processes are truly random or not is a difficult philosophical question. I don't think it has been decided. This is the question essentially if God knew, and God knows, right? If God existed, let's say, and he knew everything about the wind speeds and the molecules and the temperature and how the dice are thrown, would God be able to predict how they will fall? And now, whatever you say is essentially a religious belief. You can say yes, because if I know everything about these dice, then I will be able to predict how they will fall. Or you can say no, because fundamentally in the structure of reality, there is some kind of non-determination. Like, for example, in quantum mechanics, you have this Heisenberg uncertainty relation where you cannot say what the speed and the position of a particle is at the same time. Not only you don't know because you're human, but not even God knows. There is no knowledge about this because these values are fundamentally undetermined. So if this was the case, then it would be impossible in principle to predict what will happen with your dice. So not even God could predict them. Now again, for us, it does not matter at this point. We are not doing quantum mechanics. We are not doing determinism or other such metaphysical questions. We are just talking about mathematical functions and probabilities. So in a truly random system, you would not be able to predict the behavior of a system, either because you don't have God's processing powers or because there is nothing to predict, but in both cases, the behavior of the system to you would be unpredictable. It would seem to be truly random. Chaotic systems now are particularly interesting. They're particularly fun to play with and to look at because they are in this area where orderly behavior changes into seemingly random behavior. They are systems that live at the edge of orderliness. They are formulas that are sometimes very simple formulas where you put in some values, and as long as the values stay in a particular range, the system behaves like a well-behaved linear or non-linear but predictable easy system that does something that you can easily say what it will do next. But when you change the values and you take a somewhat different value, suddenly the behavior of the system becomes totally unpredictable. It looks truly random, and you cannot say what it will do next. And these are systems that develop from order to chaos. Chaos here just means I cannot predict what will happen. It looks random to me, but it's not random fundamentally from the beginning. It's a system that develops towards chaos. And there is a range of inputs, there's a domain of this function in which the range is orderly, and there is another domain in which the range is chaotic. And the fun is to explore exactly this transition from orderly to chaotic. A very simple function for this is called the logistic map function, and I will show you here is the formula for that. It's a function that develops a system over time. So you have time steps, and you have x, which is some variable, and this variable x you can look at some different time steps. So the first time you have an x indexed with 0, x0 means the first x with which you start. And you just give it a value. x0 is, let's say, the number 2. And now, to find the next iteration, you take this x0, which here is the x indexed with n, xn, multiplied with a factor called r. And r, we will see in a moment, is a kind of reproduction rate, if this was a biological system, or it is just a constant, just see it as a constant value. And then I also multiplied with 1 minus xn, the inverse kind of the complementary value of x. So I multiply x with 1 minus x, and then I multiply it with another constant. And this is a very easy to understand function. You wouldn't expect that this does anything interesting, but it does. And if you calculate this, it gives you x plus 1, gives you the next value of x. So now you have the next value of x plus 1, and you put this into the right side of function as the next input. So you say, this is now my xn. And I do again the same calculation, get another x plus 1, which, from the beginning now it would be x plus 2. And then I take what comes out and stick it again into the formula and get x plus 3, and so on. So I get a series of x's that come out of this formula. What is the series? And it turns out whether the series is linear or nonlinear or chaotic or predictable depends on the value, among other things, of x, the starting value, and of r. Let's see how this behaves. Here is code that does exactly this. I have my parameters, my growth rate, which here is 3.5. We'll see in a moment why it's growth rate. Just ignore it for a second. I start with 3.5, or even better, I start with 2. And then I have my x0, my initial x 0.5, and I have 100 iterations. So I go through this formula, always calculating an x and putting it again into the formula 100 times. And here's my formula. This is r times x times 1 minus x. This is exactly the formula we saw before. I generate the sequence and I plot it. So now let's do that. And look down here, it's my map. What happens with my value? Probably what you expect if you don't know about this function. It just will stay at the same place, right? You just put in something and it always stays 0.5. It never changes. Now that's not very interesting. Let's try with a different r. If I say r 2.5, does it change anything? Ooh, something changed. We get a higher value, and also we get a part of this function where it is in the beginning going out of this final value, but then converging relatively quickly to the final value. Let's take a still bigger number, 2.9. And then you see that we have more of this behavior. Now it oscillates more at the beginning and converges slowly towards the 0.6.5 value. And now I can take an even bigger value, let's say 3.5. What do I expect to see? And now you will see something that you don't expect, because now it does not converge anymore. Now you have a regular sequence of 4 different values, 2 positive and 2 negative values, and the function jumps between them. You see how it jumps from one to the next. So it's first the high positive, then the high negative, then the low positive, then the low negative, then the high positive, then the high negative, and so on. Forever. The values never change. There are these 4 values, and the function jumps between them all the time. And this is now unpredictable. You wouldn't guess this from seeing the function. And it's not all this function can do, because if I change it further and I take the value 3.9, now you see it becomes completely random. Now you don't even have this pattern. Now you don't have all the same values. Every value is different. It does not resemble, every cycle does not resemble the previous cycle. Here you have some small values in between. Here you have 2 peaks of small values, one after the other, and then again bigger values. The distances between the bigger values are not regular anymore. They change. The value of these actual values is always different. So this is now has become random. And so just by changing in this simple formula, one factor, right? You have this formula, you just change the r, you can make this function from a totally boring linear function that gives you one line that doesn't do anything, through a series of intermediate steps. First a converging function, then a function that stays and oscillates between 4 different values, and then you can make it explode into this totally random thing. So why is this useful? We will talk about this in the next video. What does this function mean? What does this logistic map mean? How did people discover it? And why do we need that? We will see in the next video.